Hello and good evening, everyone. This is Cody, your today's host. It has been, I don't know, a few months now that I made a video. I'm quite occupied with my PhD, so please forgive me if I don't have the time, but I really have to finish it. And yeah, nonetheless, I need something different now, and that's the reason why I thought, come on, do a small video. Don't expect me to be well prepared for today because I'm like pushing pretty hard on my PhDs. So I'm not, yeah, as Illidan would say, I'm not prepared. um, Nonetheless, I got something really nice today. The last video I made was about simulation data analytics. Now, today I want to show you another tool. Like last time I talked about AZ Mindset, which is a commercial tool, obviously. And this is kind of something I found during my PhD. It's like this, you scan the internet and you find this beautiful little pearl and you're like, how could I have missed this? And I felt the same way when I met Orange Data Mining, which is an open source tool for data mining. And it's really great for peeking into, I don't know, any data. It doesn't really matter. It doesn't even matter that we are simulation engineers or whatsoever. It's a really, really, really good tool to look at your test or simulation data. Now, what does Orange actually do? It provides, not only visualization, it's very, very, it has the same spirit as AZ Mindset, but I think it has more features, which is really funny because it's a non-commercial tool. I think it was developed at the University of Ljubljana. I'm not sure anymore because many other people are contributing, that's a nice thing about the internet. So I won't talk too much about it. Let's get started. The cool thing is you can install it. Obviously it's for Python or written in Python. Some people always say, hey, come on, it's just, I'm always making Python only videos. Indeed, I know many more programming languages, but the problem is just that for science, yeah, most libraries are in Python, and I think it's a great thing to have one programming environment in which you can do almost anything you want. Now let's skip this. We want to install it. You can simply install it via pip. I'm just making this to ensure that I'm taking the right Python environment -m, and then I launch the pip and then install Orange. Pew, pew, pew. And here we go. Oh no, it was not Orange. Very good that I did that I did this mistake. I'm doing it every time. It's Orange 3. The library is called Orange 3. It's very confusing because when you import it, it's called Orange, which is so confusing. But I don't know why they insisted on naming it Orange. Nonetheless, so let's start. You launch it by doing, let me clear this out once more. Yep. You start it like a module, so you launch -m orange canvas. -m simply means, for all of those who don't know what this option for Python means, it's kind of in this module or whatever, which I have installed, there is a file called canvas, and I want to run it the same way as I would run another file somewhere on my file system. So this kind of says run this module file. And we do so, and this module file launches the GUI. Here we are, and this is already the GUI. You can make a new data set here. And yeah, so they fortunately have some predefined data sets. So I have no time doing this with some other data. So let's select the iris dataset. For all of those of you who don't know the iris dataset, here it is. It's a flower dataset. So it's kind of the standard dataset for data mining classification. So you have these on the right these 3 types of flowers, and they are 3 different types. This is the iris setosa, this is the versicolor, and the last one is the virginica. And they're pretty hard to distinguish by eye, but what people did was measure, or this biological person, whatever, he measured 4 properties here, and then he kind of also noted down what type it was. And the idea is to see kind of something like a pattern in these properties here, to predict what type of flower it really is. So this is a classification property. Classification is when you want to predict a discrete label, which is either this flower, this, or this. So this is a classification problem, which is kind of like discrete regression. And here we go, we have the data set here. So what you can start off with visualization. So here we go. We open a scatter plot, and we have 4 attributes which are hard to visualize because 4 dimensions. I don't know if you ever tried. If you make a 4-dimensional plot, please send it to me because I'm really curious how 4-dimensional plots are looking like. So here we go. I simply select 2 or 3 attributes, and you see the color is the class of the flower. Now, when you watch, for example, these attributes, you see, okay, the blue color here, or the blue class, the versicolor, no, it's the setosa. The blue ones are the setosa. They are very good separable via some attributes, but you see these ones here, they are pretty mixed when it comes down to properties. Now, it depends on which properties you choose, because here in this property view, of course, the blue ones are very, very far away. They are really, it's clearly how to choose these values, these 2 properties to isolate these. But here, those 2 little beauties are touching each other, which I think is fine, you know, if they like it. But we still want to distinguish who is who. Yeah, this is the task. Like, I only have these 4 properties, and I want to predict a new flower given from its properties. It's kind of like you want to make an app which tells you what type of flower this is. So here we go. Scatter plots are pretty boring. What you can also do is visualization is tremendous. I will only show you a few nice things here. This is kind of like, we have these, this is like a histogram. We have these 3 classes, and each of them has these 50 samples. So we have in total 150 samples and 50 for each class. And you can go through these attributes, and what you see is the probability distribution of the properties. So for example, the setosa has a very, like in the scatter plots, it's very similar, not similar, but yeah, it has similarities to the scatter plot. So what you see that the setosa has a typical, very low petal width. Like the probability of a setosa. Okay, let's do it that way. The mean value of the petal width for a setosa is like 0.22, something like this. Yeah, and you can do this for all attributes and try to find some which are good or bad. Like you see here, this attribute, red and green, for example, are almost overlapping pretty heavily, and also blue is not that good separable. So you see this attribute is not very good, this one is much better, and this also. So this is kind of like a probability view, and the cool thing is, you must think of it, it's a smoothing, what you see here, of the probability distribution, and you can choose how strong to smooth it. Like, this has a very low smoothing width, and this has a very large smoothing width. So keep in mind that you see when you adapt that sometimes you can get a more clear view onto the data, like here, that it's much better separable than if you would choose here a larger smoothing. Keep that in mind. Very cool. So we can visualize. Of course, there are many more visualization techniques in data mining. I won't go into them. You can find out yourself. So let's do some prediction. So we want to train a prediction model. And I would say let's start off with my little beauty, the decision tree. Now, a decision tree, I will show you in a second what it actually does. But it tries to, from the properties, it's just a model which tries to predict the target class from the properties. So we have a decision tree, and of course, a decision tree, the problem is you can hardly peek inside, but we can use a tree visualizer because a decision tree is a white box model, so you can look inside it. And this is really cool. Like, a decision tree is making decisions, and it is making these decisions. It takes an attribute, like it takes the whole data set, then it says, okay, I take the pedal length, and when I separate or choose the threshold value 1.9, then I can kind of get rid of the iris setosa. I can kind of predict all iris setosa, 50 of 50, and then I only have to do find out how to predict the versicolor. And then with some further splits from other attributes, or the same, doesn't really matter, it can kind of isolate more kind of regions of trust. And I can visualize this further. Where is it? I think I need a scatter plot. Let's use this one here. Pew pew! No, let's make a new one. Let's make a new one because we can spare it. Pew pew! Oh, come on. As I said, I'm entirely unprepared. It should basically show up because I already used it sometimes. Here we go. Here we go. This is the decision tree. Oh, maybe it was this problem? Oh, I'm so good. Not really, but I need to tell me this so I don't cry. So you can kind of select these leaves and you see what the decision tree sees. So this is the whole data set. And now it says, okay, I take the, what was it, pedal length? Yeah, it's this one. So it chooses a split value along this, which is probably not the best. It should choose it maybe here in the middle, but we are not using support vector machines here. And what then happens is, kinda, it can isolate all the, setosa, so it makes a cut here. And then you only have to deal with these ones, and then it's hard for him to find a split. So the next split is actually here. So it tries to cut it through here. So you have only, above you have only the green ones, and below it then you have only the red ones, and then it does another split. Now when you watch the decision tree, kind of the quality, for example, you see here this leaf has only 3 of 3 samples. It has a 100% prediction accuracy, but it's pretty bad to have only 3 samples inside of it because it's rather unreliable. This one is even worse. So I would say if you drop in a new sample and the tree parses it through and it lands in this here and says it's green, then you're most probably fine. But when it goes through in such a leaf, you should be very careful. I think this branch here is not reliable when you predict a new sample. And this is a really cool thing because when you, like I said, drop a new sample in, then it just passes through and ends up in a prediction leaf. You can evaluate this. So we have this tree, and we can even inspect it. Yay! And yeah, where do we have it? And you can compute a test score. I think we first have to do, I'm not sure, is this already doing, yeah, it's doing cross-validation. So this is doing cross-validation, and we can simply plug it in and can see how well the tree is doing, if it would be working right. Do I have to do it this way? I'm not sure. no. Test score was working this way. I'm very, very sure. Pew. We can also do, maybe I will add some other techniques. Just ignore these from the names. I won't explain them how they work. But it's just about, yeah, I know what the problem was. I didn't give it any data. You have to give it the data. I thought it would get the data itself. By the way, really nice GUI, isn't it? I really love it. So now you can plug in all of your prediction models. Yeah, it's okay. And what you kind of get is this view. No, not this view. This view. It does a k-fold cross-validation, and here it's a 10-fold. And what it does is it kind of computes prediction criteria. If you don't know them, the most important ones are well known are maybe the F1 score or the precision and recall, which is kind of like how well. Let's take the precision. I'm pretty sure you know what precision is. I don't want to get into details what the difference is. And as you can see, decision trees is already has a precision of 94%, which is quite fine. The naive Bayes classifier is not as good. It has only 85.7%. And the support vector machine is slightly better than the decision tree. You can really easily add new models like the random forest, which is just multiple decision trees. Pew pew pew. And the cool thing is, yeah, it's fine. It simply recomputes automatically. And here we go. We also have only 94% precision, the same way as the decision tree. So we didn't really improve it with multiple trees. But really nice. So you can see, you can easily evaluate these ones. What you also want to do is often to evaluate a prediction model is use a confusion matrix. Oh, do I have to plug it here? Oh, okay. A confusion matrix which says how it classified right. For example, yeah, let's take the naive Bayes. The naive Bayes predicted from the 50 Iris Setosa, it predicted all 50 to be Iris Setosa correctly and not of the other classes, which is perfect. When you go to the versicolor, you see from the 50 samples, 42 were predicted right and 8 were predicted wrong, because from the Iris versicolor, 8 were predicted to be Virginica, which is wrong. And otherwise, from the 50 Virginica, 7 were predicted versicolor, which is also wrong. And you can watch this confusion matrix, which hopefully will not confuse you, but it confused me in the beginning, in order to see sometimes you have something like this class prediction is wrong, way off, and the other ones are fine, or something like that. So a little bit confusing. You can also, by the way, plot this, like get the samples out which are classified wrong. Really, really cool. There are more techniques. I think this was about prediction. I want to show you some more stuff. Dimensionality reduction. For those of you who don't know it, dimensionality reduction is kind of a technique to show high-dimensional data. For this data set, it's pretty boring because we have only four dimensions in total. But the idea is kind of when you have more than 3 dimensions, which are obviously hard to plot. When you, like I said, if you manage to plot more than 3 dimensions, please send me the plot. I really want to take a look at it. And you want to use something like dimensionality reduction. What it does is very simple. It computes the distances in the high dimensional space and tries to preserve them in a low dimensional space like 2D and 3D, and so you can plot the largest differences. And the most simple one is PCA, which is kind of like only a linear combination of features, and it tries to find the best ones. And we can plot this. Also, what happens here? Yeah, I love you. And you can see the x and y axis are called principal components, which is in this case here a linear combination of the 4 attributes which we have in the dataset. As you can see, it tries to select these 2 attributes in such a way that it can find, kind of preserve the largest differences. It's very boring for 4-dimensional sets. They use this for phase similarity when you want to visualize the similarity between faces and images. Really, really cool feature. We can also do this with other models. My dear lover's favorite, multi-dimensional scaling. Here you see the same picture, kinda, but this is a more nonlinear dimensionality reduction technique. So you can see, okay, we can barely separate it here along these ones here. Very interesting. And many, many more exist. I think, yeah, here we go. Pew, pew. Yeah, some need a little bit longer. This is T-SNE. Whoa, sorry, honey. This is T-SNE, which is from, it's pretty famous because it was quite a rush. When it was developed from a professor, I don't know exactly where, not a professor, is he a professor? No, I think he's working at Facebook. I haven't found it out yet. Must look it up. Really shame on me because T-SNE is so famous. Yeah, they use it for word similarity, visualization, and images also. But like I said, you can also choose the MDS. T-SNE is a little bit difficult to trigger because you have these parameters, and which they don't give you here, unfortunately. Yeah, but you see there are different dimensionality reduction techniques which make it sometimes easier and sometimes harder. Here maybe you can find a good cut. Nothing more about dimensionality reduction. Finally, we come to the last one I want to show you, which is clustering. Clustering is something, let's say we have these 4 attributes and we don't have the classes and we want to find kind of groups within it. So you can go in, you can simply tag it. No, you cannot. What is going on? Let's do k-meets. K-meets is awesome. Yeah. So you kind of ask it, okay, how many clusters are most probably in it, and it helps you to give you a score for this, how many clusters it suggests. The problem is determining the number of clusters. It's really, really confusing because you want to get out the number of clusters, but usually you don't know the level of detail you want to have as a user, so it's hard for the algorithm to determine the number of clusters. So in the end, you end up like getting suggestions and you simply choose them. So here it is suggesting 2 clusters, which makes a lot of sense. Let's see if we can visualize it. Yeah, okay, so it is suggesting 2 clusters, which are these 2. And you see already that these 2 are not very smartly chosen. So yeah, these 2 are wrong clusters, I would say. Do not align very well. You see here that these are only 2 clusters, which obviously makes sense, but we have this separation in here, which he doesn't know. And I think we can simply increase here the number of clusters. And here you go. This is kind of like what the clustering algorithm separated, and this is what the classes really are. And it's pretty close, not perfectly here. You have some, this one is not very well, this, and so forth. But yeah, it's already quite nice. So this really helps you to restructure your data clustering. I think this is already the end. There are much more features in here. I tried almost all of them. Not entirely. You also have rule mining, but therefore you have only to have, like in the old story, discrete attributes, which really makes no sense for CA engineers, but that's another story. You have really many techniques, and like I said, the really surprising thing is not many non-commercial tools have all of these features in such a nice environment. You know, like drag drag it in here, and it's connected and whatever. It's really nice. You don't get something like that so easily. So use it, try it, and yeah, these guys did a really nice job. So for me, it's now time getting some rest. Tomorrow is another day for my PhD writing. Yay! If you like the video, subscribe. If you don't like it, just don't subscribe. But also don't flame me. I'm just a poor man out there. I really hope this tool can help you. It helped me with my data so far. And yeah, have a nice day. I love you all, and please forgive me that for the next 2 months I will not be posting or making videos too much. See ya.